Swayam Prabha. Digital India. Educated India.
Let us start with Tresca criteria. Okay. What this criteria tells us is the maximum shear stress in the body, which is given by 1 half maximum of absolute value of sigma 1 minus sigma 2, absolute value of sigma 2 minus sigma 3, absolute value of sigma 3 minus sigma 1 should be lesser than or equal to kappa, where this is a material parameter, just like Young's modulus or Poisson's ratio. Okay. So, basically now how do you find this material parameter? You have to do some experiment to find this material parameter. So, typically we have been using uniaxial experiments to find the Young's modulus and Poisson's ratio. So, we will use the same experiment to find this parameter. Okay. So, let us say the body began to yield or began to fail at a stress when this uniaxial stress reached sigma y, okay, called as the yield stress of the material. Okay. So, let sigma y represent uniaxial stress when yielding or failure occurs. Failure here means yielding essentially occurs in the material. Okay. Now, what is this kappa? How is this kappa related to sigma y is the question. Okay. For uniaxial state of stress, I know that the stress tensor is given by sigma uniaxial 0 0 0 0 0 0 0 0 0. Okay. So, for this the principal values sigma 1 is sigma uniaxial and sigma 2 and sigma 3 are 0. Okay. So, the maximum shear stress tau max is given by sigma uniaxial by 2. Okay. So, the kappa is when this uniaxial stress reaches sigma y. So, kappa would be sigma y by 2. When the uniaxial stress reaches sigma y, the material has failed. So, that is my limiting value of that kappa value. Okay. So, kappa has to be sigma y by 2. Okay. Now, having found kappa, now I can use this to estimate what will be the failure load in shear. For example, I do a torsion experiment. I know that sigma for torsion experiment is given by 0 0 sigma x z 0 0 sigma y z sigma x z sigma y z 0, right. Okay. In particular, if I am interested in finding a point where it is parallel to where the shear stress acts parallel to the y axis, for example at a point along the x axis, then I will have this goes to 0 and I will have only that. Okay. And let me say this is tau and let me say this is tau, the shear stress acting magnitude of the shear stress acting at that location. Okay. So, I have a state of stress which is pure shear. So, you know that the Mohr circle for this is centered about the origin and it has a diameter, it has a radius of tau. Okay. So, for this case from the Mohr circle you can read out that sigma 1 would be tau, sigma 2 would be minus tau and sigma 3 would be 0 or the principal stresses for this stress state. Okay. and for this test state tau max would be 1 half maximum of 2 tau, tau and tau, right. Okay. So, this will be maximum of that will be 2 tau divided by 2 will be tau. Okay. This has to be lesser than or equal to sigma y by 2, right. Okay. So, now you have found the condition on the shear stress in terms of the uniaxial yield stress that you found from a uniaxial experiment. So, this tau in terms of torque is given by T by J into R, where R is the radial location of the point. Okay. I am interested in the maximum shear stress. So, it will be R max, the maximum value of the radial location. This has to be lesser than sigma y by 2, or my torque must be less than or equal to sigma y by 2 R max into J. Okay. That gives you the limiting torque that a circular shaft can see when it obeys the Tresca criteria. Okay. Now, I can find kappa not necessarily from a uniaxial experiment, I can find kappa even from a shear experiment, right. I can do the ulta now. I can use the shear experiment to find the kappa value and uniaxial experiment to find what is the limiting uniaxial stress. Okay. Then let us see what happens. Okay. Now, say I am giving you that tau y is the maximum shear stress before yielding occurred. Okay. Then I have tau max for pure shear is given by tau. Okay. This should be lesser than or equal to tau y. So, your kappa, this is equal to your kappa. Okay. In that case, my uniaxial, if I go back and predict my uniaxial state of stress, then I know that tau max for uniaxial state of stress is this. Tau max for uniaxial state of stress is this. This should be limited to tau y now. So, basically if I use this to predict the uniaxial state of stress that is possible, tau max for uniaxial state of stress is sigma uni by 2 must be lesser than or equal to tau y. Okay. In other words, this implies sigma uniaxial stress must be lesser than or equal to 2 times tau y. Okay. So, I can use any one experiment to estimate kappa. Once I estimated kappa, I can use that estimated value of kappa to predict the stresses in any other state of stress. Okay. Okay. Next, we are interested in plotting the failure envelope for the Tresca criteria. Okay. Let us assume that the state of stress is plane. I am interested in plotting the failure surface for Tresca criteria. Okay. What I am interested is not the general case, but plane state of stress, plane stress state. So, sigma is given by sigma xx, sigma xy 0, sigma xy, sigma yy 0, 0, 0, 0. This I can equivalently represent as sigma 1 0 0 0, sigma 2 0 0 0 0. Okay. For this, tau max is given by 1 half maximum value of absolute value of sigma 1 minus sigma 2, absolute value of sigma 1, absolute value of sigma 2. Okay. Now, what will this be? This will be equal to sigma 1, okay, absolute value of sigma 1 if sigma 1 is less than sigma 2 and sigma 1 is greater than 0 and sigma 2 is greater than 0, or sigma 1 is less than 0 and sigma 2 is less than 0 and sigma 2 is less than 0, right. Okay. When sigma 1 is positive and sigma 2 is positive, sigma 1 minus sigma 2 will be lesser than sigma 1 or sigma 2, because I am subtracting two positive numbers. Okay. So, whichever is greater will be the value of maximum stress there, 1/2 of that maximum stress. Sigma 1 is greater than sigma 2 here. Okay. Sigma 1 is greater than sigma 2, the maximum value of these tau max would be the maximum value of sigma 1 or sigma 2. Okay. Similarly, if sigma 1 is less than sigma 2 and the same conditions are satisfied, it will be 1/2 of sigma 2, absolute value of sigma 2. Okay. On the other hand, if sigma 1 is positive, if sigma 1 is greater than 0 and sigma 2 is less than 0, then sigma 1 minus sigma 2 will be the maximum value, because they are of opposite signs. So, they will add up rather than they getting subtracted. Okay. So, now it will be 1/2 maximum of sigma 1 minus sigma 2. Okay. So, with this results, now we are in a position to plot the yield surface. Let us assume that this is sigma 2 axis, this is sigma 1 axis. Okay. And I know that kappa from uniaxial stress condition is sigma y by 2. Okay. So, basically if I do a uniaxial test, the yield stress is sigma y. I can do a uniaxial stress in one direction or two direction, then the yield stress will remain same as sigma y. Okay. So, from that argument I get this point as sigma y, and similarly this point would be sigma y, okay, along the two direction, okay, where the other component of stress is 0. Okay. When both sigma 1 and sigma 2 are positive and of the same magnitude, then also I will get sigma y as my state of stress, the failure state of stress. Okay. So, I get it, I get this point in equal biaxial state of stress will still fail at sigma y. Okay. Because sigma 1 is less than sigma 2 until sigma 2 reaches sigma y, and I have both of them go in the same rate also, both reach sigma y simultaneously, and that will be a failure scenario here. Okay. So, that will be sigma y there. I did not distinguish between tension and compression, because only the direction of the shear is going to change between tension and compression. Okay. That is why there is absolute value coming in here. Okay. So, in compression also I will have the same sigma y as the failure stress and sigma y as the failure stress there, and hence this will be the failure envelope in tension and compression zones. Okay. What happens in tension compression zone? Basically, let us look at a special case wherein I was interested in pure shear. Pure shear is a case wherein sigma 1 is equal to sigma 2 minus sigma 2 equal to tau, right, wherein I had tension and compression coming in the different directions. Okay. So, since sigma the magnitude of tension and compression are same, that will represent a 45-degree line here, will represent this 45-degree line here, where the sigma 1 is minus sigma 2. Okay. In that line you know that the maximum stress that it can reach is sigma y by 2. Okay. The maximum stress that it can reach here is sigma y by 2, maximum stress that it can reach here is this is sigma y by 2 and this is sigma y by 2. Okay. And I know that the equation that governs when sigma 1 is positive and sigma 2 is positive is sigma 1 minus sigma 2 equal to sigma y. Okay. In other words, this equation is of the form x equal to sigma y plus y. Okay. So, the equation of this line is what I represented here. It is this line represents sigma 1 minus sigma 2 equal to sigma y. Similarly, if sigma in the other region where sigma 1 is positive and sigma 2 is negative, the absolute value would be sigma 2 minus sigma 1 equal to sigma y, and hence it will be this line. This line is what that equation represents. Okay. So, the Tresca criteria, the failure surface is in the form of an hexagon. Okay. Okay. So, the failure surface for Tresca criteria is in the form of an hexagon. Now, we have estimated the failure surface, that is the stress state is within this region, it is safe. If it is on the surface, it has begun to yield. It turns out that no material can cross this surface, and still it is not possible for a stress state to cross this surface. Since it is a yielding surface, okay, it is not possible for the materials to cross this surface. Okay, so, this is an unsafe region, but technically there can't exist stress states which are in this region. In this region there can be no stress states, in this or in this region there can be no stress states possible. Okay. Next, what we want to see is, we want to see in what plane the body would have failed. Okay. We have found the failure stresses, but how will the body fail is what we want to see next. Okay. So, let us take the example of a uniaxial tension, okay, surface of failure in the body. Okay. That is, we said that when tau max occurs it will fail, right. Now, what we are interested is finding that surface where tau max occurred. So, that will determine the surface of failure. Okay. For example, if I take a uniaxial bar, a bar subject to a uniaxial state of stress, a bar subjected to uniaxial state of stress sigma sigma. Okay. You know that from the Mohr circle, this is the shear stress, this is the normal stress. This is where you connect with what you have done previously. Okay. For this, the Mohr circle is, you can't forget what you have done previously, would be like that, and you know that 0 and sigma are the maximum and minimum normal stresses in the Mohr circle, and tau max is sigma by 2 that we found also occurs at a 90-degree orientation from this plane. A 90-degree orientation, the Mohr circle corresponds to a 45-degree rotation. So, basically if I segment this by a 45-degree cut, I know that the shear stress here is maximum. Okay. And hence this body will fail by shearing along this region, it will shear off along this region. Okay. Shear off along that region. So, the failure surface would look like some region is going to slide like that. Okay. Now, what happens is, once it begins to slide, it shows large deformations. So, what called as necking occurs, okay, necking occurs, and hence the final failure surface of a body in tension, for example for a material like steel, would look like this. Would look like this, okay, where there will be considerable deformations and the cross section area would reduce significantly, and this is called as necking. This is called as necking. Okay. Now, this is how a brittle material will fail. Okay. Now, let us look at another case wherein I subjected this bar to a torsional moment. Subjected this bar to a torsional moment. Okay, I fix this let me look up a case where I subject a bar, fix this end, subject it to a torsional moment T. Okay. Now, when I subject this to a torsional moment, the maximum shear stress occurs where maximum shear stress is in the plane of the problem. Okay. So, the state of stress is pure shear 0 0 0 0 0 tau 0 tau 0 for example, okay, and the Mohr circle for this is sigma of n taus of n shear stress, it will be a circle there, okay, where this is tau, this is minus tau, this is tau max. Okay. In the given plane the maximum shear stress occurs. So, what will happen is here the surface, when I twist it, these are the surfaces which are in torsion, which are in shear. So, they will just shear off like this. Okay. In torsion what will happen is the surface will shear off like that. Okay. That is if the shear stress were to govern the failure theory. Okay. Now, let us say this material was like a chalk piece which is not ductile, but it is a brittle material. Okay. Then what happens, say maximum normal stress or the Rankine failure criteria govern the failure. Okay. Then and let us say the material is weak in tension. Okay. Then what happens, this stress is what is going to cause it to fail. Okay. Then the failure surface for this has to be at 45 degrees to the direction of this shear, right. So, if I take an element here, if I take this element in from here and blow it up, I will have shear stresses acting like this, and this diagonal is going to be in tension and this diagonal is going to be in compression. Okay. Since this diagonal is in tension and the material is weak in tension, cracks will develop along this direction. This will be the crack. This is tension diagonal, this is the compression diagonal. Okay. So, the crack will develop perpendicular to the tension direction because tension causes the surfaces to be cracked. Okay. If I add tension along this direction, the crack will open up like this. Okay. That is, it will be parallel to the compression direction, compression diagonal direction. Okay. So, this you know from Mohr circle that this tension and compression occurs at 45 degree inclination to the axis of the beam. Okay. So, now let us take a chalk piece and check whether this thing happens. Okay. So, I have this chalk piece, so I am twisting it, you can see that the failure envelope is roughly 45 degrees, failure envelope here is roughly 45 degrees. Okay. So, that shows that whatever we are studying makes some practical sense also. Okay. So, what we have seen in this lecture is we have formulated the failure theory. Okay. We have said that the failure theories can be stress based or strain based, but stress based failure theories are preferred, the reason we saw, and then we saw that there are two kinds of materials which are hydrostatic pressure sensitive and hydrostatic pressure insensitive materials, and hydrostatic pressure sensitive materials behave like a ductile failure, show a ductile kind of a failure, or the shear stress will govern the failure mode, whereas a brittle material the normal stresses or a combination of normal and shear stresses will govern the failure mode. And we saw one example of hydrostatic pressure insensitive failure criteria or the yield criteria, which is the maximum shear stress or Tresca criteria, and we saw what the failure surface is and how to determine the surface along which the body will fail. Okay. We will repeat the same things for the other 4 failure theories that we want to study as part of this course. Okay. Thank you.